In class 12th P block elements, we were discussing about group 15 elements, and in this video we will discuss about preparation, properties and usage of dinitrogen and ammonia. First of all, dinitrogen, that is N2. Preparation. Dinitrogen is produced commercially by the liquefaction and fractional distillation of air. Okay. Liquid dinitrogen, its boiling point is 77.2 Kelvin, distills out first, leaving behind liquid oxygen. That is, from fractional distillation we can separate the dinitrogen from air. In the laboratory, dinitrogen is prepared by treating an aqueous solution of ammonium chloride with sodium nitrite. Ammonium chloride is NH4Cl. Sodium nitrite, NaNO2. Reaction is taking place. It produces N2 with water and NaCl. It can also be obtained by the thermal decomposition of ammonium dichromate. Its formula is NH4 twice Cr2O7. When it is heated, it produces nitrogen. Very pure nitrogen can be obtained by the thermal decomposition of sodium or barium azide. This from barium azide, BaN3 whole twice. When we heat it, we will get nitrogen. This is N3. This is azide, barium azide. And if you are asked to write the equation from sodium azide, then formula of sodium azide will be NaN3. Okay, NaN3. You can write equation yourself. Properties. Dinitrogen is colorless, odorless, tasteless and non-toxic gas. Two stable isotopes of nitrogen are there, nitrogen 14 and nitrogen 15. It has very low solubility in water, 23.2 cm³ per liter of water at 273 Kelvin and 1 bar pressure, and low freezing and boiling points. Dinitrogen is rather inert at room temperature. Why inert? Because of high bond enthalpy of nitrogen-nitrogen triple bonds. But reactivity increases rapidly with rise in temperature. At high temperatures, it directly combines with some metals to form predominantly ionic nitrides, and with non-metals covalent nitrides. With metal, ionic nitrides are formed, and with non-metal, covalent nitrides are formed. See, few examples are there, like when it reacts with the lithium, it forms lithium nitride. When it reacts with magnesium, it forms magnesium nitride. It combines with hydrogen at about 773 Kelvin in the presence of catalyst, that is Haber process, well-known process. Many times this we have discussed about the Haber process. It is used for the manufacture of ammonia. N2 plus 3H2 gives 2NH3. Dinitrogen combines with the dioxygen only at very high temperature, about 2000 Kelvin, to form nitric oxide, that is NO. N2 plus O2, it gives 2NO. Uses. The main use of dinitrogen is in the manufacture of ammonia and other industrial chemicals containing nitrogen. For example, calcium cyanamide, CaCN2. It also finds use where an inert atmosphere is required. For example, in iron and steel industry, inert diluent for reactive chemicals. Liquid dinitrogen is used as a refrigerant to preserve biological materials, food items, and in cryosurgery. That is, we can say that is any surgery or any medical treatment is done at the low temperature, then that is called cryosurgery. Ammonia. How can we prepare? Ammonia is present in small quantities in air and soil, where it is formed by the decay of nitrogenous organic matter. For example, urea. Formula of urea is NH2CONH2. When it reacts with the water, it forms ammonium carbonate and it decomposes to give ammonia. On small scale, ammonia is obtained from ammonium salts, which decompose when treated with caustic soda or calcium hydroxide. Caustic soda means NaOH. This is called NaOH. Okay. And when this ammonium salts like ammonium chloride, when reacts with the calcium hydroxide, it forms ammonia. When ammonium sulfate reacts with this caustic soda or NaOH, it forms ammonia. And on large scale, as we already discussed, this is manufactured by the Haber process. Okay. And this is the setup for Haber process. Flow chart for the manufacture of ammonia. This is H2 and N2 passed. Then this is compressor. Okay. And when this gas is passed after the compressor with catalyst, iron oxide and potassium oxide, then reaction is taking place and we will get the mixture of N2, H2 and NH3. This NH3 is condensed and we will get the liquid ammonia, and remaining N2 and H2 will again pump in the reaction mixture. Clear? Now again, if you see the reaction of manufacturing of ammonia by nitrogen and hydrogen, this is a reversible reaction and this is an exothermic process. Then according to Lee-Chatler principle, what are the optimum conditions for the production of ammonia? Okay, that is high pressure is required, and this is about 200 atmosphere. In Pascal, this is 200 into 10 to the power 5 Pascal. And temperature, low temperature should favor according to the Lee-Chatler principle, but at the low temperature rate of reaction is slow. That's why we will use the moderate temperature of about 700 Kelvin. And catalyst, iron oxide with small amounts of Ke2O and Al2O3 to increase the rate of attainment of equilibrium. These are the optimum conditions for the manufacture of ammonia. Now properties of ammonia. It is a colorless gas with pungent odor. Its freezing point and boiling point are 198.4 and 239.7 Kelvin respectively. In solid and liquid states, it associated through hydrogen bonds. That accounts for its higher melting and boiling points than accepted on the basis of its molecular mass because of hydrogen bonding. Ammonia molecule is a trigonal pyramidal with nitrogen atom at the apex. This is trigonal planar and it has the 3 bond pairs and 1 lone pair of electron. This is highly soluble in water and its aqueous solution is weakly basic due to the formation of OH minus ion. You can see this is NH3 plus H2O. It forms NH4 plus and OH minus ion. Simply when ammonia is dissolved in the water, it forms ammonium hydroxide NH4OH. This ammonium hydroxide forms ammonium salts with acids because this is basic in nature, and when react with the acid it forms salt like NH4Cl, ammonium sulfate, etc. As a weak base, it precipitates the hydroxides or hydrated oxides in case of some metals of many metals from their salt solution. For example, when this is treated with the zinc sulfate, we will get the white precipitate of zinc hydroxide. Okay, and when this is treated with the FeCl3, you will get the hydrated iron oxide, that is Fe2O3.XH2O. It will come in the form of brown precipitate. The presence of a lone pair of electron on nitrogen atom of ammonia molecule makes it a Lewis base. Okay, and it donates the electron pair and forms linkage with metal ions, and formation of such complex compounds finds applications in detection of metal ions such as Cu2 plus and Ag plus. You can say this equation Cu2 plus, blue in color, when react with the NH3, it will convert into the deep blue complex CuNH3 4 2 plus. Actually this is a one complex or coordination compound. More detail we will discuss in the coordination chemistry. Separate chapter is there. Ag plus, this is colorless. When react with the Cl minus, we will get the white precipitate of AgCl. But when this white precipitate of AgCl is treated with the ammonia, we will get the aqueous solution of this, again coordination complex, which is colorless. Okay, usage of ammonia. Ammonia is used to produce various nitrogenous fertilizers like ammonium nitrate, urea, ammonium phosphate, ammonium sulfate, and in the manufacture of some inorganic nitrogen compounds, the most important one being nitric acid. And liquid ammonia is also used as a refrigerant. Okay, students, thank you.